This video tutorial focuses on conversion of units using dimensional analysis. So students, stick around, watch, and learn. The conversion unit that we're going to use is what we call dimensional analysis, also known as the factor label method for converting units. A sequential application of conversion factors in fraction forms arranged so that any dimensional unit appearing in the numerator and denominator can be cancelled out until only the desired set of dimensional units is obtained. For example, 10.0 miles per hour can be converted to meters per second by using a sequence of conversion factors as shown below. So 10 miles per 1 hour is converted to meters per second first by providing the conversion factor, where 1 mile is equivalent to 1,609.344 meters. Also, the conversion factor 1 hour, which is equivalent to 3,600 seconds. Alright, so the units mile gets cancelled as well as the unit hour. And we are only left with the desired unit, which is meter per second. So we then multiply the quantities in the numerator, that is 10 times 1,609.344 times 1 all over 1 times 1 times 3,600, and we shall get 4.4704 meters per second, which when rounded off to 3 significant digits, the answer is 4.47 meters per second. So for our first question, question number 1, supposing you're asked to convert 3.5 meter cube to centimeter cube. So we write down 3.5 meter cube and we multiply this by the conversion factor so that later on we will be able to cancel out meter cube. Alright, the first conversion factor is in 1 meter there are 100 centimeters. Since the given unit is meter cube, then if you're going to get the cube of 100 centimeters, that becomes 10 to the 6th power centimeter cube, and that is equivalent to 1 meter cube. And as shown, the unit meter cube gets cancelled, so that our answer would be, we simply multiply 3.5 times 10 to the 6, then divide it by 1, and we will get 3.5 times 10 to the 6 centimeter cube. Notice also that we apply the rules on significant figures. Our original quantity contains 2 significant digits. Alright? So our final answer should also contain 2 significant digits. For question number 2, suppose we are asked to convert 65 kilometers per hour to meters per second. Alright? So we write down 65 kilometers per hour and then multiply this by the conversion factor where the unit kilometer is written in the denominator, while its equivalent in meter, which is 1000 meter, is written in the numerator, so that we will be able to cancel out the unit kilometer. And also, to convert hour to second, we multiply by the conversion factor where 1 hour, which is written in the numerator, divided by its equivalent in second, 3,600 seconds. And then we do the cancellation of the units. Kilometer gets cancelled as well as the unit hour. And we are left with the desired unit, which is meter per second. So we just multiply the quantities in the numerator, that is 65 times 1000 times 1 all over 1 times 3600. And we will get as our answer 18 meters per second. Again, retaining the number of significant figures in our original quantity, where there are 2 significant digits, so our answer also has 2 significant figures. Question number 3. The density of mercury at 0 degrees Celsius is 13.6 grams per centimeter cube. What is its equivalent in kilogram per meter cube? So our solution, we write down 13 grams per centimeter cube, and then we multiply this by the conversion factor where 1.00 kilogram is equivalent to 1000 or 10 to the third grams. We put 10 to the third grams in the denominator so that eventually we'll be able to cancel out the unit gram. Now for centimeter cube, our conversion factor is that in 1.00 meter cube, there are 10 to the 6 centimeter cube. Again, we write 10 to the 6 centimeter cube in the numerator so that eventually we'll be able to cancel out the unit centimeter cube. So the unit grams cancels out as well as the unit centimeter cube. That means we'll be multiplying the quantities in the numerator, which is 13.6 times 1.00 times 10 to the 6 all over 10 to the third times 1.00, and our answer would be to 2 significant figures, or I should say 3 significant figures. It will be 1.36 times 10 to the 4th kilogram per meter cube. And question number 4, the normal air pressure is 1.01 times 10 to the 5th power Newton per meter squared, which is actually also equivalent to Pascal. Question is, convert this to pounds per inch squared, or PSI. So our solution, we write down the given air pressure expressed in Newton per meter squared, which is 1.01 raised to the 5th power Newton per meter squared, and then multiply this by our conversion factor where 1.00 Newton is equivalent to 0.225 pounds. Then we cancel out the unit Newton. We also multiply the whole thing by the conversion factor 1.00 meters squared, which is written in the numerator, all right, so that the meter squared that we have here in the denominator and this one in the numerator will be canceled later on. All right, now 1.00 meters squared is equivalent to 39.4 inches squared. So, as expected, meter squared gets cancelled out. And what we'll get for our answer is the product of 1.01 raised to the 5th power multiplied by 0.225 and then multiplied by 1.00 all over 1.00 and the square of 39.4, which is 14.6 pounds per square inches, or PSI. Question number 5. You're given 1 angstrom is equal to 10 raised to the negative 10 power meters, and that 1 Fermi is equal to 10 raised to the negative 15 meter. What is the relationship between these two units, angstrom and Fermi? Option letter A, 1 angstrom is equal to 10 raised to the 5th power Fermi. Letter B, 1 angstrom is equal to 10 raised to the negative 25 power Fermi. Letter C, 1 angstrom is equal to 10 raised to the negative 5 Fermi. And letter D, 1 angstrom is equal to 10 raised to the 25 power Fermi. For our solution, we convert 1 angstrom to its equivalent in meters. So we multiply it by the conversion factor 1 angstrom. In 1 angstrom, there are 10 raised to the negative 10 meter. Notice that the unit angstrom is written in the denominator so that it can be cancelled later. There you go. And then we multiply this by the conversion factor 1 Fermi, or in 1 Fermi there are 10 raised to the negative 15 meters. Again, our task is to be able to convert meters. So we put 10 raised to the negative 15 meters in the denominator so that we can cancel the unit meter. And therefore, we are left with the quantity 1 times 10 to the negative 10 times 1 Fermi all over 1 times 10 to the negative 15, and our answer, therefore, after simplifying, you'll get 10 raised to the negative 10 divided by 10 raised to the negative 15 Fermi, and that is equivalent to 10 to the 5th power Fermi. So therefore, our answer to this question is option letter A, 1 angstrom is equivalent to 10 to the 5th power Fermi. We're down to our last question, question number 6. A certain fuel-efficient hybrid car gets gasoline mileage of 55.0 mpg or miles per gallon. Question letter A. If you are driving this car in Europe and want to compare its mileage with that of other European cars, express this mileage in kilometers per liter. Use the conversion factors 1.00 mile is equal to 1.60 kilometers and 1.00 gallon is equal to 3.80 liters. Question letter B. If this car's gas tank holds 45.0 liters, how many tanks of gas will you use to drive 1.50 times 10 to the third kilometers? So we convert 55.0 miles per gallon to its equivalent mileage in kilometers per gallon. First, by multiplying this by the conversion factor of 1.00 mile equivalent to 1.60 kilometers. We put 1.0 mile in the denominator so that we can cancel it later. We then multiply to this the conversion factor, which is 1.00 gallon is equivalent to 3.80 liters. Again, since we want the unit gallon to be cancelled, so we write it in the numerator. And if we do the cancelling, we'll have the mile gets cancelled and the gallon gets cancelled. So 55.0 miles per gallon is equivalent to 23.0 kilometers per liter, which is our answer to letter A. And in answering letter B, we make use of our answer in letter A, all right, which suggests that 23.0 kilometer is the distance that you can travel using this car having a volume of gasoline equal to 1 liter. And that is equated to 1.50 times 10 to the third kilometer over the unknown volume of gas in liters. And transposing this equation so that we will be able to have the formula for finding the volume of the gasoline in liters, we have V is equal to 1.50 times 10 to the third power kilometer to be divided by 23.0 kilometers per liter. And what we will get is a volume equal to 65.0 liters. Notice that the kilometer unit gets cancelled. And since we're asked to find how many tanks of gas, okay, will the driver use to drive that distance of 1.50 raised to the third power kilometer, we simply divide this volume 65.0 liter by the amount of gas of 45.0 liter, and our final answer is 1.40 tanks of gasoline will be used up. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.